everyone, welcome to Math 104. We're working on sections 4.1 and 4.2 today. Our topics will be integer exponents and scientific notation. To start things off, I'd like to show you where these rules that we're going to be using come from. So what I'm going to do here is just use the definition of exponent to expand out 3 squared and 3 to the 4th power. So we get 3 times 3, and then 3 to the 4th is 4 3's multiplied. So the product then is all of these 3's multiplied together. Well, we have 6 of them, so that's 3 to the 6th power. So how do we go from 3 squared times 3 to the 4th power and get 3 to the 6th power? We're going to use this formula. A to the m times a to the n is a to the m plus n. So we just add together the exponents, 2 plus 4, and get 6. Same thing works with variables, x to the 5th times x to the 3rd power. We got 5x's here, 3x's here, we get x to the 8th. 5 plus 3 is 8. So when multiplying exponential expressions, add the exponents. Quotient rule, expanding 2 to the 7th, we have 7 2's on top. 2 to the 3rd gives us 3 2's on the bottom. So what we'll do next is go through and cancel. Pairs of 2's, 2, 2, 2, 2, 2, and 2. What do we have left? We have 4 2's on top. So 4 2's here gives us 2 to the 4th. So how do we get 2 to the 4th? 7 minus 3. 7 minus 3 gives us 4. We can do the same thing with variables, x to the 6th, x to the 4th. We're going to cancel matching pairs of x's. So those cancel, those cancel, those cancel, those cancel. What do we have? We have 2 left. X times x, or x squared. So 6 minus 4 gives us 2. That leads us to the quotient rule for exponents. A to the m divided by a to the n is a to the m minus n. So when dividing exponential expressions, subtract the exponents. Finally, power rule for exponents, and there are a couple of different power rules. I'm going to call this power rule A. We've got 2 to the 3rd to the 4th power. So I'm going to expand what's inside the parentheses first. 2 to the 3rd. 2 times 2 times 2, still to the 4th power. So 4th power means we have 4 of these things multiplied. So here's 4 of them. And notice now we have 12 2's all multiplied together. That is 2 to the 12th power. So where does 12 come from? That's 3 times 4 gives us 12. So the power rule, we have a to the m times 8 or to the n power. Multiply m times n. Same thing works with variables, x to the 5th to the 3rd. That's 5 x's to the 3rd power. So 3 of those, or we have 15 x's. So that's x to the 15th power. So 5 times 3 gives us 15. These are some of the most important rules of algebra, so make sure you have these formulas down. And if you ever forget, just use the definition of exponents, expand them, and you can figure them out. Notice that these rules only work when we have the same base. 2 is the base here, 2 is the base here. If we had 5 to the 3rd down here, we wouldn't be able to do any canceling. So let's look at some examples with some real numbers in here. X to the 7th times x to the 4th. This is the product rule, so we're going to add those exponents together and get x to the 11th. So these rules are a nice shortcut. We don't have to expand or anything like that. We just add the exponents together. Second example, x to the 7th divided by x squared. That's x to the 7 minus 2, or x to the 5th. Last one, we get x to the 3rd to the 6th. So that's x to the 3 times 6, or x to the 18th power. Your turn, number 1. So part A, we have x to the fifth over x to the third. That's x to the 5 minus 3 by the quotient rule. X squared. Next one, product rule, x squared times x to the 8th. That gives us x to the 2 plus 8, or x to the 10th power. Part C, x to the 4th to the 5th. That's x to the 4 times 5, or x to the 20th. Now in the next example, we've got some expressions where there are multiple variables. Make sure you're only combining the variables with the same base. In this one, we're going to be multiplying x to the 3rd, y to the 5th times x squared, y to the 4th. So we're going to combine the x's together. That's x to the 3 plus 2. And then y to the 5 plus 4. So that gives us x to the 5th power and y to the 9th. Next one, x to the 6th, y to the 9th divided by x, y to the 7th power. So we'll subtract the exponents on the x. Remember, x without an exponent is just x to the 4th power. So we got x to the 6 minus 1 and y to the 9 minus 7. So that gives us x to the 5th, y squared. Your turn, number 2. First one, we're going to combine the x's, x to the 5th times x to the 7th, that's x to the 5 plus 7, or x to the 12th. The y's, y to the 1st times y to the 6th, that is y to the 1 plus 6, or y to the 7th. Next one. Now we're doing quotient rules, so we'll subtract these exponents. Combining the x's, we have x to the 8 minus 3, and then y's be 4 minus 3. And that is x to the 5th times y. Now in all these examples with the quotient rule, we've had exponents in the numerator that are larger than the exponents in the denominator. Well, let's look at a couple of cases where that does not happen. So in this case, we have x to the 5th over x to the 5th. That's x to the 5 minus 5, or x to the 0 power. Well, what's the value of anything divided by itself? That's 1. 2 divided by 2 is 1. X divided by x is 1. X to the 5th divided by x to the 5th is 1. So that means x to the 0 has to equal 1. Next up, we'll do one where the denominator is greater than the numerator. So that's x to the 3 minus 5, which is x to the negative 2 power. So let's figure out what this negative 2 power here means. And I'm going to show that by expanding this. So you've got 3 x's on top and 5 on the bottom. So I'm going to start canceling x's here. That one's gone, that one's gone, that one's gone. And so what do we have left? We've canceled everything on top, so that means we have a 1 on top. Remember, once you're done canceling, that leaves us a 1, not a 0. And the bottom, we have x to the second power. So that means x to the negative 2 must equal 1 over x squared. And that is indeed the case. And that brings us to the definition of 0 exponent and negative exponent. So for any number to the 0 power, we'll define that as being 1. A to the negative n equals 1 over a to the n. And then the reverse of that is a to the n equals 1 over a to the negative n. Now keep in mind that anything can be written over 1, so just consider these to be a to the negative n over 1. So this a to the negative 1 is in the numerator. And when we move it to the denominator, we change the sign on the exponent. Same thing happens here. We can go from negative to positive or from positive to negative. So whenever you have an exponential expression and you move it across the divisor line, change the sign of the exponent. So to help you remember, when you cross the line, change the sign. Here's some examples of what we can do with these properties. Seven over x to the negative 4 power. I can take this from the denominator, move it to the numerator, and change that to be a positive exponent. So that gives us 7x to the 4th power. Another example, we have 5x to the negative 3 power. Now I'm going to take this. Remember, this is automatically in the numerator if there's no fraction, because we can always write it over 1. So this is in the numerator. I'm going to move it to the denominator and change that to a positive exponent. The 5 has nothing to do with that exponent. Remember, the exponent only applies to the thing next to it. So the 5 stays in the numerator. And x to the 3rd goes in the denominator. The exponent becomes positive. Your turn, number 3. So the first one, we've got this in the numerator. We're going to move it to the denominator. The 6 stays in the numerator. So that becomes 6 over x to the 4th power. And with this one, we're going to take this and move it up into the numerator alongside the 2. That becomes 2x to the 3rd power. We've got 2 more power rules. These will come up all the time. I'm going to call these power rules B. In words, what's going on here is if we have an exponent on some expression inside parentheses, we have to apply that exponent to every factor inside the parentheses. We call it factors of things that are multiplied together or divided. So we're going to apply this to the a and also apply it to the b. So we get a to the n, b to the n. And this works no matter how many things we have inside the parentheses. If we had a, b, c, it'd be a to the n, b to the n, c to the n. Over here, same thing works with both the numerator and denominator. We're going to apply the exponent to the numerator to get a to the n. We'll apply it to the denominator to get b to the n. And the same thing applies if we have multiple things in the denominator. If we had bc in the denominator, it'd be b to the n, c to the n in the denominator over here. So apply it to absolutely everything you see. Examples. 2x to the 3rd power and 3 over y to the 4th power. The mistake I see here is people saying this equals 2x to the 3rd power, only applying the exponent to this thing. You have to apply it to everything inside the parentheses. So this becomes 2 to the 3rd, x to the 3rd. In this one, we're going to apply the 4 to the top and the bottom. 3 to the 4th over y to the 4th. And then we can go ahead and evaluate these numbers. So 2 to the 3rd gives us 8, so we got 8x to the 3rd here. And the bottom 3 to the 4th is 81, so we get 81 over y to the 4th power. Your turn, number 4. So we're going to apply the 2 to the 4 first, 4 squared, and then to the a squared. 4 squared is 16, so we got 16a squared. Apply the 3 to the numerator, that's b to the 3rd. Apply it to the denominator, we get 3 to the 3rd. So that gives us b to the 3rd over 27. Next up, some rules for negative exponents. So these are just some of the other rules combined together in different situations. So here we've got a couple of negative exponents. What we can do is just flip them and turn both exponents positive. All right, we're going to move this one to the numerator. Exponent becomes positive. This one to the denominator. And the exponent becomes positive. Next one, we've got a shortcut. We could use 2 different rules to do this in 2 steps. Then we'll see the shortcut. So what we would do here is take this, apply it to the numerator. So we get a to the negative n. Apply it to the denominator, we get b to the negative n. Then we do what we did up here. Switch them and turn them positive. So that is b to the n over a to the n. All right, so that's the long way. What we can do here is just flip the fraction over. And there's our second rule. So what this one says is if you have a fraction to a negative exponent, you can flip the fraction, becomes its reciprocal, and the exponent becomes positive. And finally, a to the negative n equals 1 over a to the n. So a little shortcut for combining a couple rules there. Next example, example 5. So applying these rules, we have different bases here. So that's like this one. Notice that a and b are different bases. So I'm going to take this, bring it up into the numerator, make the exponent positive. So there's 2 to the 4th on top. 5 to the negative 3, that goes in the denominator and becomes 5 to the positive 3. Now we can evaluate the top and the bottom. 2 to the 4th is 16. 5 to the 3rd is 125. 16 125ths. For this one, we're going to use this rule here. Fraction to a negative exponent. Take the reciprocal of the fraction, make the exponent positive. So that is 5/4 to the 3rd power. Now we can apply the exponent to the numerator and denominator separately. So 5 to the 3rd over 4 to the 3rd, 125 over 64. Your turn, number 5. The first one, I'm going to take that, bring it down to the denominator. Exponent becomes positive. 3 goes up top, exponent becomes positive. Evaluating, 9/4. I'm going to flip this fraction here, turn it into 3/2. Still, or change the negative exponent to a positive exponent, so we got to the 4th power there. That becomes 3 to the 4th over 2 to the 4th. 3 to the 4th is 81. 2 to the 4th, 16. 81/16. We're going to see now some examples that show combining multiple properties into one problem. Example 6. First thing we do is apply the quotient rule. X to the third over x to the seventh, that is x to the 3 minus 7. Y to the fourth over y squared, y to the 4 minus 2. Subtracting here, we get x to the negative 4th power, y squared. Now, in order to be fully simplified, we have to get rid of all negative exponents. So I'm going to take this and move it down into the denominator and turn the exponent positive. So this becomes y squared. The y squared stays on top. X to the 4th goes on the bottom. Final fully simplified answer is y squared divided by x to the 4th. Your turn, number 6. Combine the x bases, we have 4 and 1, so x to the 4 minus 1. The y bases 2 and 7, so that's 2 minus 7. X to the 3rd, y to the negative 5th. And finally, we'll move this to the denominator, keeping the x to the 3rd on top. Turning that exponent positive, we get x to the 3rd over y to the 5th. Example 7. X, y to the 4th, all to the 3rd power. So we're going to use power rule A, apply this exponent to everything inside the parentheses. So the x and the y to the 4th. So we're going to x to the 3rd, y to the 4th to the 3rd. Applying power to a power. We'll multiply those out, we get x to the 3rd and y to the 12th. Your turn, number 7. X to the 3rd times y to all to the 5th power. Using power rule A, x to the 3rd to the 5th. I'm sorry, power rule B, x to the 3rd to the 5th. That means power rule B says apply this to all factors inside the parentheses. So you got x to the 3rd to the 5th and y to the 1st to the 5th. Now we use power rule A, power to a power. X to the 3 times 5, y to the 1 times 5. That gives us x to the 15th and y to the 5th. Now we're going to look at some more complex expressions and fully simplify them. So the procedure for fully simplifying some sort of exponential expression is to evaluate all the numbers and then create a fraction if possible and simplify that fraction fully. Next up, we're going to combine any exponential expressions that have the same base. And then, finally, we're going to get rid of any negative exponents. Example 8. We got 4x squared over y to the 4th, all to the 3rd power. So we can apply that exponent to both the numerator and the denominator. Okay, now we use power rule B, apply it here, apply it to every factor inside the parentheses, so 4 to the third, and x squared to the third. And here we've got power to a power. 4 times 3 is 12. Just write it as 4 times 3 this step. 4 to the third, that is 64. X squared to the third power is x to the 2 times 3. Multiplying those exponents out, we get 64x to the 6th over y to the 12th. When I'm doing these, I'm going into a lot of detail, showing every step. It may not be possible to show all of this. Make sure you're showing all the properties, though. Your turn, number 8. So to apply the 4 to the numerator and the denominator. Now we can apply it to both things on the bottom here. And x to the 5th to the 4th, that's going to be x to the 20th. So a little more concise way of doing it this way. 3 to the 4th times y squared to the 4th. That gives us x to the 20th, or 3 to the 4th is 81, and y squared to the 4th, 2 times 4 is 8, so that is y to the 8th power. X to the 20th over 81, y to the 8th power. Example 9. All right, now we've got something to the negative exponent. So the first thing I always like to do is get rid of that negative exponent. You can go ahead and apply the negative 4 to everything inside the parentheses, but then you're going to get a bunch of negative exponents. You're going to have to move them across the divisor line. It's a lot more steps and it leads to a lot more mistakes. So might as well just get rid of that negative exponent right from the beginning. We'll flip that fraction over into its reciprocal and turn that positive. So we get y to the 5th over 2x to the 3rd power, all to the 4th power. So another way of writing this out is just go ahead and apply the 4 to everything inside the parentheses at once. So I applied it to the y to the 5th here, I applied it to the 2 here, and I applied it to the x to the 3rd here. Now, power to a power, we're going to multiply those exponents, so we get y to the 20th on top. On the bottom 2 to the 4th is 16, x to the 3rd to the 4th, 3 times 4 is 12, so that is x to the 12th power. Y to the 20th over 16, x to the 12th. Your turn, number 9. First step, take the reciprocal of the fraction, make the exponent positive. Now we'll apply the 3 to the 6 first, 6 to the third, apply it to the y to the fourth, y to the fourth to the third, apply it to the x, x to the third. That gives us, let's see, 6 to the third, that's 216. Y to the 4 to the 3, that is y to the 4 times 3, or y to the 12th power, all over x to the third. 216, y to the 12th, over x to the third. All right, next up, we're going to see an example where we're going to put all this stuff together into one problem. And that is the ultimate goal in this course, is to be able to do a problem of this complexity. We'll do it by breaking it down into little pieces that are like the examples we've seen so far. So we're going to simplify this entire expression. And so we've seen problems like this before, and we've seen problems like this before. We just haven't seen them all together at once. So what you can do is just work on these individually, and then combine them if you like. That's a nice way to simplify things. So with this one, first step is I'm going to get rid of that negative exponent by flipping the fraction over. Notice nothing changes inside the fraction. That negative exponent, it stays negative. This one stays positive. The only sign that changes is the one on the outside. And this one, just leave it. All right, now we can either use the definition of negative exponent here to move this down here. But as we'll see later, we don't really need to do that because we're going to get rid of that negative exponent when we combine it with this y over here. So I'm just going to apply the exponent straight up to everything inside the parentheses in both of these. So apply it to the 5 here. That becomes 5 squared. Y to the negative 3 squared, that is y to the negative 6. Multiply those exponents together. Down here we got x to the 4th squared, that is x to the 8th power. Over here we've got y to the 4th power to the 3rd power, that's y to the 12th. 4 to the 3rd is 64, and x to the 1st power to the 3rd power, that is x to the 3rd. So we've done power to a power on all the exponentials, and just apply the exponent straight up to the numbers. So I can go ahead and write this as 25. And now let's put those two numbers together in a fraction. So we got 25 on top and 64 on the bottom. Now we can combine these two y exponentials, y to the negative 6 and y to the 12. They're both in the numerator, they're going to stay in the numerator. And we'll add those exponents together using the product rule. On the bottom, we have x to the 8th and x to the 3rd. We'll combine those two together. That's x to the 8 plus 3. They're both in the denominator, so they're going to stay in the denominator. Now we've got 25 times, combining these together, you get y to the 6th. And on the bottom, we have 64. X to the 8 plus 3, that is x to the 11th power. So 25 y to the 6th over 64 x to the 11th. Your turn, number 10. And there are a lot of different ways to do these, depending on which order you use the properties. So I'm going to apply this exponent to all three things inside the parentheses here. Y to the 5th to the 4th. Power to a power, we have 5 times 4, or y to the 20th. Over 2 to the 4th is 16, stays in the denominator. X to the 3rd to the 4th, 3 times 4 is 12, that is x to the 12th. Now this one, we're going to flip this fraction over. So we get 4 y to the negative 7 over x to the 5th, and then we're going to change the sign on this to positive. Now we can apply this exponent to everything inside here, so this thing isn't going to change at all. Still got y to the 20th over 16, x to the 12th, and over here, 4 to the 3rd, that's 64. Y to the negative 7 to the 3rd, you're going to multiply those two together to get negative 21. So we got y to the negative 21. And then x to the 5th to the 3rd, that's x to the 15th. So we're multiplying fractions, going to multiply straight across. 64 will stay on top. Y to the 20th times y to the negative 21. Add those exponents together, we get y to the 20 minus 21. 16 stays in the denominator. Now we'll combine the x's. X to the 12 times x to the 15. That's x to the 12 plus 15. Now we can reduce this fraction. 64 divided by 16 is 4. You get 4 there. Y to the 20 minus 21 is y to the negative 1. Combining 12 and 15, we get x to the 27th. Last thing we need to do is get rid of that negative exponent. So I'm going to take this expression, move it down to the denominator, and turn that exponent positive. So our final answer is 4 over x to the 27th, y. Now our next topic is scientific notation. So with scientific notation, we're going to take some number between 1 and 10, not including 10, and multiply it by a power of 10. So for example, we could write 517,000 in scientific notation. So what we want to do now is take the exponent where it starts, just the right of the last number, and move it until we get to a number that's between 1 and 10. So 1 space 2, 3, 4, 5 to the left gets us between the 5 and the 1, 5.17. So that's between 1 and 10. So that's where we want to go. 1, 2, 3, 4, 5. Quite get that right. 4, 5. There we go. And so if we moved it 5 places, we're going to multiply by 10 to the 5th power. However many places you move the decimal, that becomes the exponent. Now if we move the exponent to the left, the exponent's positive. If we move it to the right, the exponent becomes negative. Your turn, number 11. So let's see how many places we have to move this one. 1, 2, 3, 4, 5 to the right. We get 5.39, and it's negative. So negative 5.39, we move it 5 to the right, so that is times 10 to the negative 5th. So notice that negative exponents give us very small numbers, little decimals. Positive exponents give us big numbers. So we got a big number here. 3, 6, 9 places, plus one more is 10. So that is 4.0489 times 10 to the, we moved it 10 spots, so that's 10 to the 10th power. 4.0489 times 10 to the 10. Next example, we're going to convert 3.48 times 10 to the negative 4 into standard notation. One way you can do this with your calculator, the x actually does mean multiplication. So you could take 3.48 and multiply it by 10 to the negative 4th, and you get some decimal answer. Another way to do it is, we have a negative exponent, so we want to make this thing smaller, so we'll move it 4 places to the left. 1 gets us to the left of the 3, and then 3 more zeros. So this would equal 3 zeros, 348. And we're 4 decimal places away from 3.48. Your turn, number 12. Convert these to standard notation. First one, we're going to move 5 to the right to make it a bigger number, since this is positive. So 1, 2, 3, 4, 5 gets us here, right between the zeros. So that'll be 207, 480.03. 207,480.03. This one, since it's negative, we're going to move 3 to the left. So 1 gets us to the left of the 7. We'll have to move 2 more. So that's 2 zeros. 0.007138. Finally, got a couple of applications of scientific notation. You're going to see this stuff all the time with things like computers, since computers have advanced so much. It's kind of hard to talk about them without using terms like gigabyte or using scientific notation. So it's estimated that YouTube receives a lot of bytes per day in video uploads. We've got 268 and then 12 followed by 12 zeros. So we might as well write that in scientific notation, because who wants to write all those zeros? So that is 2.68 times 10 to the 14th bytes. That's how many bytes of data they receive in video uploads per day. And now if you have a really nice internet connection, which I don't have, but you can download somewhere in the neighborhood of 50 million bytes per second, which is 5 times 10 to the 7. And so we're going to calculate how long would it take to download 1 day's worth of YouTube videos. So we can divide those out, and make sure you can perform calculations like this in your calculator. Some calculators will have an E symbol, and some of them have a 10 to the symbol on there. So figure out how your calculator works. Divide these out. Bytes divided by bytes per second is seconds. So that gives us 5.36 times 10 to the 6th seconds. Well, that's a whole lot of seconds and not particularly meaningful. So let's break it down into something that makes a little more sense. So we're going to convert seconds into hours, first of all. So there's 1 hour equals 3,600 seconds. So there's our conversion factor. We can multiply those out. So this is the effect of taking this number divided by 3,600. And that gives us 1,489 hours. And we can do one more conversion, see how many days this is. So 1,489 hours over 1 times 24 hours in 1 day. So we'll take 1,489 divided by 24, and we get about 62 days. Quite a download. Your turn, number 13. Apollo 11 traveled at about 1.656 times 10 to the 4th miles per hour while in orbit. The distance to the sun is 9.3 times 10 to the 7th miles. How long would it take Apollo 11 to reach the sun? So we'll divide 9.3 times 10 to the 7th miles, the distance to the sun, divided by the speed, 1.656 times 10 to the 4th miles per hour. Divide those out. We get 5,615.9 hours. So let's see how many days this is. All right, there's our conversion factor, 24 hours in one day. Take 5615.9 divided by 24, and we get approximately 234 days. All right, that's it for today, everybody. Go practice your properties of exponents.